So, good afternoon, everyone. Welcome to the third class of reagents in organic synthesis. In this class, we will discuss about some reducing agents. So, first, we will discuss about or summarize about the batch reduction. So, batch reduction is a reaction where aromatic ring or saturated ring being unsaturated in presence of sodium or lithium in liquid ammonia condition. So, here you can see that in presence of any electron donating group such as methoxy, methyl, isopropyl, or in condition of batch reduction, lithium liquid ammonia. So it forms this kind of alkene. Or in presence of any kind of electron withdrawing group in batch reduction condition such as acid, ester, amide. So these are all electron withdrawing group. These are all electron donating group. So we are seeing that different electron donating effect or withdrawing effect giving different type of dying in batch reduction condition. So this can be explained the mechanistic viewpoint. So what happens in the batch reduction condition is that first any kind of metal such as sodium and lithium in liquid ammonia condition. So we all know that metal can donate its one single electron and form the metal ion charge. So it can donate the single electron and form the solvated electron ammonia complex. So now in presence of any group which has electron donating group, so it the electron undergo ortho attack to the electron donating group position. So which form this radical. Now this as radical in presence of any kind of alcohol or any kind of proton source such as methanol, ethanol, or tert-butanol, any kind of proton source from this complex, the single electron transfer process proceeds through and giving this product. Whereas in presence of electron withdrawing group, the attack happens through the para position. So the single electron transfer through para position and give this anion with further single electron process give this anion. So why this is giving this anion and the electron donating group giving this anion and electron withdrawing giving this anion. So we can explain it. So why the single electron transferred in electron donating group in ortho position or electron withdrawing group in para position. So what happened here? So in presence of any electron withdrawing group, such as this one, I am writing acid. So it forming this anion. If it happened through para single electron transfer. So it formed this anion. So now this anion can stabilize. Now this anion can stabilize by the carbonyl group of the electron withdrawing group. So now this through the resonating conformation. So what happens here? This is stabilized through resonating structure. That's why the single electron attack in the para position for electron withdrawing group. But if it attack in the para position for electron donating group, such as this one, so we'll get
Excuse me, sir.
yes,
Sir,
yes,
can you repeat it once more?
okay. So, so I'm clearing this first. So what happens is there, if it is an electron withdrawing group and donating group, so the activity is different. In case of electron withdrawing group, the single electron forming the attacking happen in the para position, or in case of electron donating group, the single electron transfer happen in the ortho position. So I am writing this example. This is O-methoxy group for para electron donating, and this is acid or ester for electron withdrawing. So if I considering this intermediate for para attack of the electron withdrawing group, so this is the forming this negative charge for the para attack. So now this negative charge undergo resonance with this ester group or electron withdrawing group and stabilize. This negative charge is stabilized. So what happens is there? So this is happening. So this negative charge is stabilized for electron withdrawing group. That's why the single electron transfer happening to para position for any electron withdrawing group. But if is electron donating group, the negative charge will if attack happen from the para position, so negative charge will come here. But it is destabilized due to the electron donating effect of this O-methoxy group. So that's why the attack is not happening through para single electron transfer for electron donating group, but in case of electron withdrawing group, the para single electron transfer happen in electron withdrawing group. So this is the reason why we are getting different type of product for electron donating group and electron withdrawing group.
Okay, sir. Then one more doubt. So why is it happening in the meta position for electron donating group? So, like, is there any stabilizing effect like that?
So if you write the uh, single electron transfer mechanism, so you will see that for case of meta position, the negative charge is not stabilized. So if we write here, so this will go, and this will form here. The radical will form here for meta. That's why we are not getting the meta selectivity for both of the cases, electron donating and electron withdrawing. So the radical stability is the main reason for the para and ortho selectivity. I think this is clear.
Ah, yes, sir. It's clear. It's clear.
So now this is the example of some Barks reduction. So here what is happening first is the lithium liquid ammonia tertiary butanol is the proton source. So first we are getting this product. So and in case of as it is electron donating group, that's why we are getting this vinyl methoxy product. Uh, in presence of acidic condition, so this will be protonated and is as acid as water, so it will attract here and release methanol, which will give this product. Now this is an undergo tautomerization reaction leading to the formation of this product. Now if you see that this ketone and this double bond is not in a conjugation form. So for the system stability, if it is from alpha beta unsaturated ketone, so this will stabilize. So that by resonating form. So that's why it undergo isomerization reaction in the temperature whatever is there 70 degrees centigrade. So in this temperature it is isomerized due to the stabilization of the system through the alpha beta unsaturated form, and it will stabilize through resonating form. So in the second example, it is also electron donating group. That's why we are getting this product. So now we'll discuss about lithium aluminum hydride reagent. So lithium aluminum hydride, the structure is this one, lithium plus and aluminum hydride is AlH4 minus. So lithium is positively charged and aluminum hydride is negatively charged. So why aluminum directly not attack in any kind of ketone? This is ketone. So aluminum is negatively charged. So in this system, aluminum should directly react to the carbonyl compound, but it's not happening because the aluminum is metal. So it metal tendencies is it tends to lose its electron. So what happened due to the dipole moment effect or aluminum as a metal, it's give its electron to the hydride or hydrogen directly. That's why aluminum in that case hydride hydrogen is forming hydride and the so it can also explained by the electronegativity. So aluminum electronegativity is 1.61 and hydrogen electronegativity is 2.21. Due to this dipole moment effect, as aluminum is metal, it tends to lose its electron. So that's why it is electropositive aluminum and hydrogen is electronegative. That's why hydride is transferred in case of lithium aluminum hydride reagent. So the example or if we explain the mechanism, so first lithium plus AlH3 minus. So one due to the electropositivity effect of aluminum, hydride is transferred, not the aluminum directly attacked to the carbonyl. So first it is attack here and O minus is formed. First is the addition of hydride to ester, then elimination happen. So this will go and water will leave through ROH. Then it will form aldehyde. Then one or whatever aluminum hydride is there, it will further attack and form this alcohol after workup. So this is the basic mechanism of aluminum hydride reaction. Now this is the sodium base 2-methoxy aluminum hydride. That is red L. It is also very important. Also, it can be called as SEMA, SMEAH, sodium base methoxy aluminum hydride. So it is also a strong reducing agent like aluminum hydride. It also reduces aldehyde, ester, amide, alkyne, both all the compounds. So this is the structure. It is also hydride source, and this is the methoxy, and this is the ethoxy group. So that's why it's called sodium base methoxy. Though two methoxy are there, two ethoxy group are there. So the application is reduction of amides, both ADAL or lithium aluminum hydride, both reduced amide to amine. So the mechanism could be, so first the hydride will attack, so it will form OH. Now elimination of water molecule giving this imine. Now further one hydride attack the imine which form amine. So this is the example of radon reaction with alkyne. So in presence of any kind of propargyl alcohol, this is propargyl alcohol, alkyne and alcohol connected to the C1 position. So that's called propargyl alcohol. So first, what happens is there aluminum as aluminum is electropositive metal and oxygen is electronegative compound. So it it will react to each other and form this kind of aluminum oxide compound. And whatever the hydride is there, so it will transfer here. So it is transferred like this way and give alkene to alkene through hydrolysis. So now this is the sodium borohydride reduction. So this is mild than LH or red L. So same concept is here. Boron is also, so if we write the sodium borohydride structure Na plus BH4 minus. So boron is, we are writing negative charge on the system of boron. We all know boron is a metal. So first, that's why it should be electropositive. And that's why it donate all its electron to the hydride source. That's and forming boron positive. That's why the hydride is transferred, not boron directly attack to any carbonyl or any kind of compound. So basically, boron is a very mild reducing agent, so it only react with aldehyde or ketone, not the other compound. So the electronegativity of boron is 2.04 and electronegativity of hydrogen is 2.20. So that's why hydrogen is more electronegative and it donates as a hydride source. So this an if we consider the example or mechanism is same like lithium aluminum hydride. So this is the hydrogen. So in presence of sodium borohydride and methanol condition, that the aldehyde reduced to primary alcohol. This is also aldehyde. So in presence of NaBH4 methanol condition, it is reduced to primary alcohol. So this is a very important reaction, Leach reaction. So in presence of sodium borohydride and sodium chloride, sodium is +3 oxidation state. It also compounds 7H2O. So sodium hydride is there, aqueous of sodium chloride. So this this combination is called Leach reduce reduction combination. So what happens is there in presence of any alpha beta unsaturated ketone. So this is alpha beta unsaturated ketone. In presence of sodium borohydride, sodium chloride. So only this and the ketone is reduced, not the double bond. So 1,2 reduction is happening. But in presence of sodium borohydride, 1,4 reduction is happening. So what is the mechanism or what is the why it is happening? So first we have to understand the mechanism for Leach reduction condition. So in Leach we used methanol or ethanol as a solvent. So what happened is there. So in presence of methanol, sodium borohydride, or sodium chloride. So, oxygen has lone pair. So as sodium is a Lewis acid, it has +3 oxidation state. So it coordinates with the methanol and one of the hydride molecule attack to the methanol. So which form methoxide ion and minus H2 is hydrogen gas will leave. So it is formed. So as boron is donate one hydride, so it will neutral BH, H, and methoxide. So we all know boron is a vacant p orbital. So it has vacant p orbital. So it can accommodate the methoxide ion in its vacant p orbital. So it will form B OMe H3 minus. So further it will react with methanol and ultimately it will form BH OMe minus. So now due to this methoxide ion and it will form this methoxide containing boron compound. So this OMe group has electron donating effect. So it will give the electron to the boron compound due to the oxygen lone pair, which makes this hydride is stronger So this is strong, not as a soft. So this hydride is very strong due to this sodium chloride and methanol reaction. So it will form strong reagent. So we all know in case of alpha beta unsaturated ketone, this position is soft and this position is hard. As this is making this methoxide ion making the sodium borohydride compound very hard, so it will react to the 1,2 pressure. So due to the sap principle, the soft hard interaction. So this hard nucleophile attack to the hard electrophile 1,2 attack, giving this secondary alcohol after reduction of 1,2 reduction. So this is the reason why Luche reduce reduction happen through 1,2 reduction. But in presence of sodium borohydride, this kind of Lewis acidic effect doesn't happen here. That's why it will behave as a soft hydride source. So due to the soft hydride source, the soft center, this is beta position, it will act. So why this beta position is soft? Because the resonating structure. So if we move the electron to the oxygen, so it will form electropositive and this will form electronegative. So that's why this due to the resonating form, this is it will form soft. So compound which are electronically biased is a soft electrophile or which is not electronically biased such as acetone. So this is not electronically biased. There is no double bond or no resonating structure can happen. So that's why it is strong or hard. But whatever has double bond or electronically biased or it can form resonating structure, it will call as soft. Due to the hard soft interaction, the Luche reduced happen in the 1,2 position. So this is the example. So here also Luche reduction condition giving this alcohol. So alpha attack happening. So this methyl group is the alpha position. So whatever the hydride source is coming from the beta position. That's why this O is going to the alpha position. So the hydride will coming as beta position. That's why we are getting this stereochemistry. Here also same alpha beta unsaturated ketone. So Luche reduction condition giving this product. This is the one more important reaction, reductive amination. So it happened through sodium cyanoborohydride reagent. This is the structure of sodium cyanoborohydride. So in presence of one hydride, there is a one cyano group. So what is reductive amination? So we all know amination reaction. So what happens is amination reaction, any kind of aldehyde in presence of any kind of amine from this imine. So this is called amination. So when this double bond is reduced or fully hydrogenated, that will call as reductive amination. So the mechanism is there. So first, so we use sodium cyanoborohydride in presence of very mild acid. So the acid activated the carbonyl compound and then amine will attack. So it is from this quaternary ammonium salt. So next this lone pair of oxygen, lone pair of oxygen attack to the acid and it will form the H2 complex. Then amine attack and dehydration happen, giving this iminium. So now sodium borocyanoborohydride comes in the picture. So it attack to the iminium compound to its hydride source and giving this unsaturated compound that is this reductive aminate product. So this is the general reactivity order of any kind of reaction. So first Any acyl halide will react, then anhydride, then an aldehyde, then ketone, then ester, then amide, and less reactivity is acid. So in this compound, if we carefully see, acid, ester, acyl
Sir,
chloride is
excuse me, sir. Sir, in the reductive amination, only NaBH3CN will give the reaction. Like
yes, yes,
NaBH4 will not
yes.
do the same.
Mostly, most of the literature we are found that we find that sodium cyanoborohydride is the reagent for reductive amination, not sodium borohydride. So this is very what we say mild reagent due to the cyano group. That's why only
Okay.
sodium cyanoborohydride reduce reductive aminated product.
Okay. Okay, sir.
Uh, Here also first SN. So the reactivity order. So if we add only sodium cyanoborohydride, so this is very mild. So due to the cyano is the electron withdrawing effect. So it reduce the electron negativity of the hydride or boron, we can say, due to the electron withdrawing effect of the cyano group. So that's why the hydride is very mild. So it can't attack aldehyde also. So that's hydride only at in case of acyl halide, only sodium cyanoborohydride reaction happen, not any other reaction. So acyl halide hydride is react and chloride is leaving group, so it is from aldehyde. So this aldehyde is not further reduced to alcohol in presence of sodium cyanoborohydride. So as we all know, aldehyde is highly electrophilic, but the electrophilicity not matching with the hydride source because hydride is very less nucleophile here or very less nucleophilicity is there in case of hydride. So that's why it's not attacking on the aldehyde phase also, not giving any alcohol. But in presence of sodium borohydride, this first it will form aldehyde and then further one molecule of hydride attack on the aldehyde, giving this alcohol. This is the reactivity order. So sodium cyanoborohydride only react with acyl halide, but sodium borohydride has react with acyl halide and aldehyde both. But lithium aluminum hydride or dead al, both are very strong reducing agents. So it will react acyl halide, acid, ester both. So first this acyl halide converted to alcohol. This acid also converted to alcohol and this ester. So in presence of lithium aluminum iodide, hydride will attack here and first it will form this some remaining all the components still. First reaction happened with acyl chloride, then this ester. So it will form this. Now one equivalent of lithium aluminum hydride or aluminum hydride as four hydride source. So this hydride also react with the aldehyde, giving the alcohol. This is the general reactivity order. So we can say acyl halide only react with sodium borohydride, acyl halide and aldehyde react with acyl halide only react with sodium cyanoborohydride. Acyl halide and aldehyde both react with sodium borohydride. And all the compound, acyl halide, anhydride, ketone, ester, amide, acid, all the compound reduced by lithium aluminum hydride because it is very strong. So now we come to the problem solving class. The first question is this one. So this compound in presence of sodium borohydride and lithium aluminum hydride, what is happen? So two molecules are there. One is the ketone, one is the ester. So we all know that NaBH4 only reduced aldehyde and ketone. So under NaBH4 condition, this ketone is reduced to alcohol. Ketone reduced to alcohol. But under lithium aluminum hydride condition, ketone reduced to alcohol. This is the first one. And then ester also, as it has ester also reduced to alcohol. So the right option will be A is good. And also here is a cyano group also is there. This is also amine. This is also reduced to CH to NH2 in presence of the cyano group also reduced to CH to NH2 in lithium aluminum hydride condition. So the whatever is true. This is will be the answer. Next question is the this one. Aldehyde. This is aldehyde. This is ketone. This is ester. So first is lithium and I'm giving only ketone. Ketone is converted to alcohol. So lithium aluminum hydride reduce all of the one ester, ketone, aldehyde, so it will not happen. Radon also very strong reagent, so it will also reduce aldehyde, ketone, ester. Sodium borohydride. The sodium borohydride we can reduce both ketone and aldehyde also, but ester remain as such. So reduced ketone and aldehyde, but ester remain as such. What happened with sodium borohydride, sodium chloride combination? So in these cases, only ketone will convert it to alcohol. Why? So we first, if we write, so first we compare the electrode positivity. So between ketone and aldehyde is more electrophilic than ketone. So whatever the reaction happens should first happen to the aldehyde position. But in these cases of sodium borohydride, sodium chloride combination, the reaction happen in the ketone position, which is less electrophilic than aldehyde. So what is the reason behind this? So what happened is there, so as sodium chloride is a Lewis acid, as sodium chloride is a Lewis acid, so I'm just writing RCHO and RCOR prime. So this aldehyde is more electrophilic than ketone. So activation of aldehyde first happen by the Lewis acid sodium chloride. So this will so now when we have done any kind of reduction, so we'll use methanol or ethanol as a solvent. So methanol and ethanol, all the solvent containing water. So due to this activation of this aldehyde, in by the sodium compound, water will attack here in presence of aldehyde. So it will form this gem diol hydrate. This is called gem diol hydrate. So in same carbon, both the diol is there. So this is called gem diol hydrate. So due to this formation of gem diol hydrate in aldehyde or sodium chloride Lewis acid, So it is reversible. So this is and it is stabilized by the cerium complex. So that's why it is stabilized. So it remain in this form in sodium borohydride cerium chloride combination. This remain in the gem diol hydrate form in the aldehyde due to the more electropositivity of the aldehyde. But as the ketone electropositivity is not that much, that's why water is not attacking here. Direct hydride source, whatever is there, is attacking here and reduce the ketone to alcohol. That's why in sodium borohydride and cerium chloride combination, aldehyde remain as such and ketone is reduced. So as this gem diol dihydrate form, which is stabilized by the cerium chloride complex, it remain in this form. Or if we localize this alcohol, so one molecule of water will release and it will form in the aldehyde. So it is a reversible reaction. That's why aldehyde remains the aldehyde, not reduced. So this is the reason. So correct answer is the sodium borohydride cerium chloride combination. Now the next question is the lithium liquid ammonia tributanol first and then NCPD. So as ONA electron donating group, the single electron transfer reaction happen through ortho position. So there is a two possibility. It will give this product or this product. So which so if it attack the single electron transfer attack through this position, the arrow will move like this way. So it will give this product or the ortho attack happen through this position. The arrow will move like this way and this giving this arrow. There is a two possibility. This is also ortho position. This is also ortho position. So with the first one giving this one and the second one giving this one. But what is the major or what is the primarily form? So it will form this one because methyl is also electron donating group. Electron donating group. So if it is attacked to the ortho position, this position, then this is also form and this is also form. But here in this cases, no ortho attack is happening. That's why we are not getting the ortho double bond product. So this is the first right product due to the electron donating effect of both methyl and methoxy group. Now they give MCPBA. So there is two double bond MCPBA metachlorobenzoic acid. So it's done. It is using for epoxidation reaction we all know. So there is a two double bond, this one and this one, which is more electronically rich double bond. So the O methoxy has its lone pair. So this is more electronically rich due to the lone pair of the O methoxy group. Resonating structure we can say, but here methyl is also electronic, it can electron donate through hyperconjugation or plaza effect. So resonating effect is much more greater than the plaza effect or hyperconjugation effect. That's why this double bond is more electronically rich. So it attack to the acid and giving the epoxide. So this will be the right answer. Second question is same like that. So there is a two possibility. Ortho O methoxy is also electron donating group. This this attack or this attack. So if this attack is happen, the arrow will move like this way, this way. So it will give. this product. This will be forming because both the double bond in the position of electron donating group. That's why this is more stabilized. So this will form this one. Now there is a mistake. So it will be methyl iodide or methyl bromide. So under electron lithium ammonia, the single electron transfer here happen. This will go and this will go this like this way. What happened? Silicon radical and one radical was taken out by the lithium complex. Then it will form diradical and that is a negative charge. Negative charge. Now this negative charge react with the methyl iodide, leaving this I, so giving this product. So para between ortho and para position of the quinoline, para attack is more facile than ortho. That's why we are getting this para attack. So this is electronically more biased, the para position. So due to the electron withdrawing effect of the quinoline. So this will be the right answer. If you have any question, you can ask.
No, sir, it's clear.
So now we go to the question number 6. Sodium liquid ammonium methyl iodide. So now this is electron withdrawing group, acid group. This is electron withdrawing. So what happens here? If we remember the mechanism, electron withdrawing cases attack happen through parareactivity. So it will form this anion, anion. So now if we give tertiary butanol, that attack with the tertiary butanol proton and this will give protonated. But here the system has methyl iodide. So that anion react with the methyl iodide and leave the iodide that give this compound. The right answer with the second one. So this is happened due to the electron withdrawing effect of the acid group. Now the next 7. So I'm writing A and B. So in case of A, the ketone is reduced. Ketone reduced to alcohol. In case of enone, the alpha beta unsaturated. Enone to saturated ketone. So, so we all know. So hydrogen palladium is carbon is the hydrogenation condition. So it hydrogenate the double bond. Any kind of alkene or alkyne under hydrogenation condition hydrogenated. So This is first not happen, and sodium borohydride also both reduce the alpha beta unsaturated ketone. So this is not happen. So sodium borohydride can reduce the alpha beta unsaturated ketone, but not happen. So this is the sodium borohydride, sodium chloride combination. Only reduce this ketone to alcohol due to the under the Luche reduction condition mechanism, and hydrogen palladium carbon only reduce this double bond alkene to alkane. So the right answer is this one. So so yeah. Now the next reaction condition is this lithium reagent plus lithium aluminum hydride. So in presence of lithiated reagents, so it is that lithium is positively charged, we all know. So it will react with the carbonic compound as carbon is electronically biased or electropositive. So first it will form this one. This one. Now lithium aluminum hydride. So previously I already told that aluminum hydride is a electronically positive compound. So it has a high propensity of reaction to any kind of alkoxide. So if I write like this way, so this alkoxide react with the aluminum and this hydride. This hydride will transfer like this way, and that negative charge after the hydrogen hydride transfer, whatever has formed, this react with the complex. So whatever is what is forming here. I'm just like writing alien. Sorry, writing I have written wrong. Okay, this is level one. Two. Okay, what happened? This hydride will attack in this position, and this negative charge will attack to the aluminum. So it will form the five-membered ring. One, two, three, four, five. So this ring will form. So now there is a possibility of pinnacle type of rearrangement. This will go, and this bond will break, react here, and leaving the chloride. It have to write combination. So first, this is forming. After that, I write aluminum. So lone pair attack with the aluminum. Hydride is transferred here, and that negative charge react with the aluminum. This is giving this 5 members pyro-unrelated product, pyro-center 5 member. Now there is a possibility of pinnacle type of reaction. Now this aluminum oxygen bond breaking and this single bond transfer here. So like pinnacle type of rearrangement. So you all know pinnacle rearrangement, right? What happens in pinnacle rearrangement? This carbon of oxygen hydrogen bond electron push here and this vinyl group directly migrate to the positively charged center. Here is the same happening is there. After chlorine liberation, it will form positively charged center. So this bond is migrating here. So it will form this one. Now the system has lithium aluminum hydride, LH. So this ketone is further reduced to alcohol. So the option, all the option is wrong here. So this is an error. So the correct answer will be this one. I think this is clear.
Sir, as the aluminum oxygen bond migrates, shouldn't it form the C double bond? Though?
Yes, it will form C double bond too.
Okay, again the
So again, lithium aluminum hydride reduce that
will
ketone to
okay.
alcohol.
Okay.
Understand?
Sir, understood.
So now the next question is this one. So SEMA is the radar. So what happened in this case? The presence of radar aluminum hydride. Two hydride is there in radar. So one hydride is transferred to this one as ester. So this will go and remove ethanol. This first form, this aldehyde, right? After hydrogen transfer. Now this aldehyde further reduced to alcohol in lithium aluminum hydride condition. Sorry, radial condition. So this aldehyde further reduced to alcohol. Now nitrogen has lone pair and oxygen has lone pair. So oxygen is coordinated with the aluminum as that is electropositive metal, oxygen is electronegative. So this will go and leave this alcohol due to the oxide, aluminum oxide formation. This will form this one. Imine. This iminium ion will form. Now this iminium is further reduced to imine in presence of radon. So this hydride later here, this will go. This will give this is nothing but methane, CH3. So methyl group. So this will be the right answer. So first, ester reduced to aldehyde, aldehyde reduced to alcohol, and alcohol is further reduced to iminium, and iminium is further reduced to amine. So this will give directly methyl from ester. So why this is happened? This is happened due to the nitrogen lone pair. If it is carbon, then it will remain in the alcohol form. As it has nitrogen, so due to the availability of the nitrogen lone pair and the availability of oxygen aluminum complex formation, this iminium is forming. That's why we are giving this product. If carbon, then it will remain in the same alcohol form. So what is the last question? So BH3 lithium borohydride. So BH3, what happened? BH3 is reduced acid to alcohol. BH3 is a very strong reducing agent. It's reduced acid to alcohol. So what happened is there. COH reduced to H2OH. So that acid is reduced to alcohol. Now what happened? Alcohol has oxygen, this alcohol has lone pair, so it will attack to the carbonyl of the ester. So this will migrate, this will go and ethanol will liberate minus ethanol. This will give this product. This one. So in BH3 condition, but what happened in lithium borohydride condition? Lithium borohydride is milder reducing agent than boron, so it will reduce ester to alcohol. What happened is here. So it will reduce to ester to alcohol and acid remain. So now what happened? This alcohol of the boron, uh, this alcohol is further activated by the boryl boryl or boron. Now this keto this the acid will react and liberated this alcohol. That will give this product. What is the right answer? A, A is this one, B is this one. So second option is the right answer. Is clear?
Yes, sir, it is clear.
So this is the 10 question what I have. from the NPTEL. So I have done. If you have any question or queries, you can ask or raise your hand, whatever is possible.
It is clear, sir. No, sir. No more questions.
Then we can stop the class. We'll see you in
Okay,
the
sir.
next class.
Okay, sir. Thank you, sir.